Yeah, but it never does.
Okay.
I have actually set to record it.
Oh, right. You should get the fireman stuff playing.
You're in the way.
It would.
Greetings, Earthlings. We are Alien Life Frequency. We're doing an impromptu freeform jam, testing our levels, just kind of doing some beats, having a little fun on Saturday night. Stay spacey.
What is it that you're doing?
Feynman is that one.
Which one?
The phone. Yeah. Just hit play.
They'd jiggle faster. They'd push back. That's what solid means. That's what hard means. The resistance of matter to being compressed is a quantum mechanical effect.
In classical physics, the best arrangement of positive and negative charges would be all of them sitting on top of each other. Everything collapsed to a point. But quantum mechanics says no. You can't confine particles to a small space without paying the price in momentum. So the next time you sit in a chair and it holds you up, that's quantum mechanics. That's the uncertainty principle, keeping you from falling through to the center of the Earth. Now here's something else that classical physics got completely wrong. Energy. In the everyday world, energy seems continuous. You can have any amount you want. Push a car a little, it goes a little. Push harder, it goes more. Smooth, gradual. Any value is possible. But in the atomic world, energy comes in steps, specific amounts, like a staircase, not a ramp. Think of a guitar string. It's fixed at both ends. When you pluck it, it vibrates, but it can't vibrate any way it wants. It has a fundamental frequency, the lowest note. Then it has harmonics, higher notes, at specific frequencies. You don't get a continuous range, you get specific notes. Same with electrons and atoms. The electron wave has to fit around the nucleus in a certain way. Only certain patterns work, and each pattern has a specific energy. We call these energy levels. When an atom is in a high energy level, it can drop to a lower one, but it has to lose that energy somehow. Where does it go? It comes out as light, a photon. And the photon carries exactly the energy difference between the two levels, not approximately, exactly. Since the energy levels are specific, the energy of the photon is specific, and the energy of a photon determines its color. So each type of atom produces specific colors of light. Hydrogen produces certain colors, helium produces different colors, sodium produces that yellow-orange glow you see in some street lamps. If you look at the light from a distant star through a prism, you see dark lines, specific colors missing. Those are the fingerprints of atoms. Each element absorbs and emits specific frequencies. By reading those lines, we can tell what stars are made of billions of miles away. All because energy in atoms comes in steps. Now let me tell you about something even stranger. Electrons refuse to be in the same state. What does that mean? If you have an atom with many electrons, they don't all crowd into the lowest energy level. That would be the most economical arrangement, right? Everyone on the ground. Pauli exclusion principle, and nobody knows why it's true. It just is. But without it, chemistry wouldn't exist.
If you guys want to
All electrons would pile into the lowest level. Every atom would behave the same way. Carbon would be like oxygen, would be like iron. No variety. But because electrons have to spread out into different levels, different atoms have different arrangements. Different arrangements mean different chemical behaviors. Carbon acts like carbon. Oxygen acts like oxygen. The periodic table, all of chemistry exists because electrons refuse to share the same state. The rules seem arbitrary. Why 2 electrons per level? Why not 3? Why not 10? I don't know. Nobody knows. These are the rules nature plays by. We discovered them by doing experiments. The rules work. They give predictions that match reality. But the deep reason? Still a mystery. Nature has rules. Our job is to discover them, whether they make sense to us or not. So where does all this leave us? We started with a simple question: what is reality? And we ended up having to throw away almost everything we thought we knew. Particles don't have definite positions until you look. They don't take definite paths. They exist as clouds of probability, described by arrows that we add together. The act of observation changes the outcome, and there are fundamental limits to what can be known, not because we're ignorant, but because nature itself is fuzzy at the bottom. This bothers people. It bothered a lot of very smart physicists. Some spent their whole lives trying to find a way around it, trying to prove that underneath all this uncertainty, there must be some hidden machinery, some deeper layer where things make sense again. So far, every attempt has failed.
Every experiment confirms the quantum picture. The fuzziness is real. The probabilities are fundamental. There's no hidden clockwork underneath. Now you might ask, if particles don't have definite properties until we measure them, what's really going on? Honest answer? We don't know. The theory doesn't tell us. Quantum mechanics is a set of rules for calculating probabilities. It tells you what you'll observe when you do an experiment. It doesn't tell you what's happening when you're not looking. Some people say the particle is in many states at once until you observe it. Some say there are many parallel worlds where every possibility happens. Some say the question itself is meaningless. We should only talk about what we can measure. These are interpretations, philosophies. They all give the same predictions. There's no experiment that distinguishes between them. But let me tell you what we do know for sure. The theory works. The theory works. The theory works.
can feel it. I can feel it.
Experiment with electrons, tiny, tiny particles, the smallest bits of matter we deal with in everyday physics. We shoot electrons at a barrier with two slits. Time an electron arrives. Each click is the same, never half a click. So electrons arrive as whole things, individual lumps, particles. Good. Electrons are particles, just like tennis balls. But now we count where they land. We build up a picture of the pattern, and it's not two clusters.
How long has that been? Oh, the card is full.